Okay, now we're at the stage where we're ready to talk about doing more than one matrix after the other. So we'll think of actually using the output of one matrix to feed to the input of another one. And this is called composition. And you may have heard of this before. It's really just function composition, but with matrices. So for example, what if I scale my vector first? So remember this was the scale matrix, right? So I scale it in x first, and then after that, I flip it in x. Okay, so one way to figure out what this is to actually just first do the scale, figure out what that is as a function of x and y, and then do the flip. So what this is like saying is put parentheses around this part, just get this part done first by itself, so do the scale, and then feed that result to the flip. And so if we do that, what we see is, okay, if I do the scale first, I get 2xy, right? And now, instead of feeding xy to this, I'm actually going to feed 2xy to it. So I'm going to feed the result of the scale to the flip. And when I do that, I see, okay, my new x is actually negative 2x. So negative 1 times 2x plus 0 times y, it's negative 2x. And then 0 times 2x plus 1 times y, that's y. And so here's the result. It's actually more exciting if I show you in the demo here. So I set this up so I can actually, okay, so the first one is 2, 0, 0, 1. We'll call that matrix A. So that's the scale in x. And then the second one, I'll call it matrix B. That's the flip in x. And so here it is. I'm writing the parentheses like that. Okay, so this is what it would be if I just scaled, and this is what it would be if I just flipped. But if I scale first, and then I flip, that's what I get. Okay. So then you might ask yourself, all right, do I get the same thing if I do them the other way around? Oh, actually, sorry, before I get to that. Okay, there's another way to do this. Actually, I can put the parentheses in another place. What I can do is actually pre-compute the result of sending the output of this first matrix to the input of the second matrix. So here's a really neat thing we can do. So we'll actually put the parentheses around those two matrices and do them first. And so here we follow the matrix multiplication rule that we already did. It's just that now we actually have to do it to two vectors instead of one. So what we're going to do is see, well, what does this second matrix do to the first column of this first matrix? So what does it do to that vector 2, 0? And what does it do to that vector 0, 1? So that's the way we can do it, right? Because we're walking along the vector 2, 0, and we're walking along the vector 0, 1. So then we can just see, well, what would happen to those vectors as we move them through. So what you can do is say, okay, well, the vector 2, 0, when I put it through this, so let's see, so negative 1 times 2 plus 0 times 0, that gives me negative 2. All right? And then 0 times 2 plus 1 times 0, that's going to give me a 0. Okay, so when I put 2, 0 through the flip, that gives me negative 2, 0. And then when I put 0, 1 through the flip, it actually just gives me back 0, 1. So here's the result. So it's like saying row 1, column 1, that's a dot product of the first row of the second matrix and the first column of the first matrix. Row 1, column 2, well, that's dot product of row 1, second matrix, column 2 of the first matrix. Okay, so and then this element would be this row dotted with this column. So 0 dot times 2 plus 1 times 0, we got that. And then this element here would be this row dotted with this column, which is a 1. But really, again, all it is just taking and seeing what happens to each of these columns in this matrix when I put them through the next one. And the really cool thing about this is you don't have to just stop at 2. You can do 100 of these in a row, and you'll just get back a 2 by 2 matrix at the end. So if you keep doing this, so you just do 2 at a time, all right? So take the parentheses do two at a time, simplify it down to one. Then do the next one. Then do the next one, the next one. At the end, you'll just end up with a 2 by 2 matrix. So even if you do this 100 times, even if you do this 1,000 times, you'll just end up with a 2 by 2 matrix at the end if you do this pre-multiply. So that's pretty neat. And even so from a computer science perspective, the fact that you can store the composition of thousands of maps with just 4 numbers is incredible. Okay, that's an incredible savings in memory right there. So now it's much easier to see, well, the result of this is just going to be negative 2xy. Okay. So that's what happens when you scale and then flip. Cool. All right. Now, I explained this all out, but you'll hardly have to worry about this because actually there are functions in GLMatrix to do the multiplication for you. So as long as you set these up properly, you can just rely on GLMatrix to do this stuff for you. But I wanted to explain some intuition about why the matrix multiplication is defined the way it is. It's because we know how to take a vector and send it through the map. So it's just taking each one of these column vectors and sending it through the map. Okay. All right, so now let's get to that question I was jumping at the gun before. So does it actually matter what order I do this in? So if I scale first and then skew, is that the same as, or sorry, if I scale first and then flip, is that the same as flipping first and then scaling? So I just switch the order of these matrices here. Let's see. Okay, so this was the scale first then flip. So that looked like this. If I flip first and then scale, that's going to look like this. It actually does give me the same answer, interestingly. So you can do this out and you'll see that you get the same answer. But in general, this is not true. So I want to have you do a quick exercise to try to find an example where this breaks down. So think of all the types of matrices we considered so far and try to find one where, or find a pair of them where if you switch the order, they don't give you the same answer. Okay.